Hey kiddos, this is your final notes video on the evolution of massive stars, which can form both neutron stars and black holes. As we've already seen, mass is the determining factor for what sort of star you end up with. Mass is also the determining factor for how those stars evolve. So we've already seen that we have three main sequence stars based on mass, and that determines where they fall on the HR diagram. And that correlates then to how they evolve as they move off of the HR diagram. In terms of stars that fall on the upper left-hand portion of the HR diagram that are greater than 8 solar masses, we have two potential outcomes, and those also are dependent on mass. But in this case, we're not necessarily looking at the mass of the initial star. We're looking at how big that core is, which of course is related to that. So our two outcomes are a black hole or a neutron star. So if we have a mass of the core that is less than 3 solar masses, so again, we're talking about the core of the star, when that infall happens following a supernova, because these are both the result of a supernova, and this is a type 2, not a type 1a, what you can have is that infall of matter, which happens at such a high rate and creates so much pressure in the interior of the star that you can have protons and electrons that can recombine to form neutrons with a byproduct of a neutrino. And a neutrino is much, much smaller than an electron. It's less than 1/1,000,000th of the size of an electron. So it's the same sort of degeneracy pressure that makes it stable, just like a white dwarf. But because neutrinos are so much smaller than the electrons that uphold the size of a white dwarf, these can be so much smaller, as we'll see momentarily. So the formation of those neutrons are what halt that collapse. Whereas when we have a black hole, this would be a stellar core that is greater than 3 solar masses. When you have that infalling of the supernova explosion that hits that iron core and rebounds outwards, nothing halts that collapse. So again, mass is the determining factor. The formation of neutrons halt the collapse into a stellar remnant of a neutron star. Greater than 3 solar masses at the core, nothing halts the collapse, and we end up with a black hole. So neutron stars are just a collapsed core remnant of a massive star as a result of a supernova. These were first recognized in the 30s, around the same time when we discovered the elements of neutrons. In the 60s, there were radio pulses that were detected by Bell Laboratories from Bell telephones, and these radio pulses were detected as they interfered with telephone lines. These were then directed towards the center of the galaxy, but at the time they were actually thought to be extraterrestrials. Obviously they weren't, but they found that there are radio pulses detected towards the center of the galaxy and also in many different places within the galaxy. And we now know that these are the collapsed remnants of massive stars. So neutron stars are composed of neutrons and neutrinos, which are electrically neutral. And these are the densest things in the universe. So just like we've talked about how white dwarfs have this incredibly high density as a result of a larger star with a given mass shrinking to a much, much smaller volume. In the case of a neutron star, we're talking about a larger mass compressed to a smaller volume, because neutrinos and neutrons can be compressed tighter than electrons. So we get neutrinos because that core is collapsing, and the formation of neutrinos and neutrons happens as gravity presses the material in on itself so tightly that those protons and electrons recombine to make neutrons. So that's how we get the name, obviously, of neutron star. And these are the most dense things in the universe. 1 teaspoon would weigh as much as 1 billion tons. And the gravity on a neutron star is 2 billion times greater than the gravity on Earth. It's strong enough to actually bend radiation from the star in a process known as gravitational lensing, which, fun fact, is actually how we detect and are able to observe dark matter. So what this essentially means is it's bending light. So astronomers are able to see around the backside of the star because the gravity of this neutron star is so great. And if we look at this image, we can see that a neutron star would be similar as a tennis ball placed on a map of a large city. In this case, it's Washington, D.C. But we could think about this as being the size of, say, Stevenson Ranch. But we've got this incredibly high density and a small radius. So here we can see this artist's rendition of the process of making a neutron star. Here we can see the giant star phase rendition of a supernova in box 2, and then in box 3 we can see our glowing bright neutron star. So neutron stars are incredibly hot, they spin rapidly, they are very, very dense, and they have incredibly strong magnetic fields. So these are hot because as this star is collapsing, then we have a supernova, that formation of neutrons at the core, and the contraction of the star as a whole then heats the gas within the star. And it's important to remember that just like in white dwarfs, we have no processes happening here. There is no thermonuclear fusion. We don't have the recombination of light elements making heavier elements. This has already happened. So this is long past that. So this is the remnant following a supernova explosion when you've already had iron at the core. So these spin rapidly due to the conservation of angular momentum. So remember that just as mass can neither be created or destroyed, matter can't either. So as we already have that star of a given mass, as it's contracting and getting a smaller volume, all of that energy and that rotational energy has to go somewhere. So that collapse then causes it to spin incredibly quickly. So these can actually spin up to 43,000 times a minute. However, they are actually slowing down. They're incredibly magnetic because the magnetic field of the original star is then squeezed into a much smaller volume, making it much stronger when that star collapses. So the average neutron star has this really strong magnetic field. We measure magnetic fields in terms of Gauss, and we think about the Earth's magnetic field as having 1 Gauss. The Sun's is a few hundred Gauss, but a neutron star is about 1 trillion Gauss. So this is much, much stronger than anything we could even imagine terrestrially. So here we have the internal structure of a neutron star. We can see these imaged magnetic field lines intersecting the poles. That doesn't necessarily mean it's the rotational axis, but that represents the magnetic field. We can see this thin atmosphere. Think about a crust, a nuclear plasma or pasta, and then the core regions. So here we can see a supernova remnant. This is taken by the Chandra Observatory, which is imaging in X-ray and in gamma rays. We can see that remnant of a neutron star at the center. This is about a 2,000-year-old supernova. As we've already talked about, we can see those ionized gases. It's about 10,000 light years from Earth. And this neutron star at the center is rotating once about every 6.7 hours. So that's indicative of this being pretty old in terms of terrestrial years, because the rotations are going to gradually slow. So the neutron star will eventually slow down, lose its magnetism, lose its heat, just as a white dwarf will. The neutron star will also die. This is not an infinite phase of the star. They do have finite lifetimes. One of the ways that we can identify neutron stars is when we observe them as pulsars. Pulsars are seen as these rotating, blinking objects at the center of supernova remnants that appear to blink or pulse on and off at regular intervals. We see these as X-ray beams that appear to emit from the polar regions of the pulsar. So these generally have periods of about 1/10 of a second to about 60 times per second, but we also see these millisecond pulsars that can have rotations of as much as 700 times per second. So pulsars are also neutron stars, but they're identified as having these X-ray pulses. And we see them as that X-ray beam then sweeps Earth. And the X-rays are produced by that neutron star that happens to be in a binary that is capturing material flowing from its more massive companion. And that material then interacts with its magnetic field, producing those high-powered radiation beams. And here we can see the Crab Nebula, which we've already looked at in multiple different wavelengths. We can see the pulsar that's at the center. This was the one that we used, that we measured the expansion of the supernova, the knots within it, to see when that supernova actually went off. So here we can see the Crab pulsar as it's pulsing on and an image of it pulsing off. So we can much more easily determine the location of that pulsar when it's on than when it's off. But these happen at regular intervals. So here we have an image of a pulsar within a binary system. So pulsars are created when you have a neutron star that is in a binary. By 2010, astronomers had detected about 1,800 pulsars through radio detection and another 70 by gamma rays. Some of these pulsars even have planets orbiting around them, and some may actually turn into planets as they slow their rotation, lose their heat, and lose their intense magnetic field. In 2011, there was a huge news story that a diamond planet was found, and then it was debunked as being what we would now call fake news, but it actually really wasn't fake news. What it was a planet that was found orbiting a millisecond pulsar, and that intense magnetic field and the gravitational pull from that pulsar had caused the carbon within that planet to crystallize into diamond, which is just the purest form of carbon when it's attached to 8 other carbon molecules. So we have these millisecond pulsars that are created when it's within a binary pair. And we've already looked at binaries as a result of a white dwarf with a more massive companion. When it steals that matter, fills the Roche lobe surrounding the star. But in this case, we can have a pulsar that gets sped up by its companion star if that companion star is greater than 10 solar masses. So you have the same process of mass transfer filling the Roche lobe that makes it unstable, and these tend to live very, very short lives. So if you have a companion star that is less than 10 solar masses, we still have that transfer and filling the Roche lobe, but it's more through the process of solar wind than physically stealing the matter and the gases from that star. So in this case, the material would flow along the magnetic poles of the neutron star and create X-ray pulsations as it was heated. We call these pulsars not because they actually pulse, but we have this spinning object that's emitting these beams of rotation that can be oriented or directed towards Earth and make it appear as though it's pulsing. So as they spin, that beam can sweep across the sky, much like a lighthouse would sweep across the sky, a lighthouse beam. And if Earth happens to be in the path, we would detect that pulse of radiation. Understanding what this model means is crucial for understanding the strength and power of what a neutron star actually is. So remember that this is only a few kilometers in radius. So we're talking an incredibly small radius, but this can produce powerful beams that can be seen across galactic distances. So the neutron star always has these magnetic field lines and always has this electromagnetic radiation. However, once it becomes excited to make the gas glow, such as in the process of mass transfer between a higher mass companion star, that's what could excite the gas, make it appear to pulse, and then if it's pointed towards Earth, it can be easily detectable. Here again is the Crab pulsar, so we have the optical field here. It looks like it's overlaid with some UV and near-infrared imagery. We can see the pulsar at the center. Here we can see in gamma rays, and we can see that period of jet forming from the rotational axis, and we can see all of these jets and winds surrounding that pulsar. And this is our Crab pulsar, which is a result of a supernova from 1054. Magnetars are another way to observe neutron stars. Magnetars are also neutron stars, but these have the strongest magnetic field of anything detected or observed in the universe. So after a supernova, if the spin, the temperature, and the magnetic field of this newly formed remnant star have to fall within the right ranges, a magnetar can form. And it's estimated that about 1 in 10 supernova explosions results in a magnetar rather than a standard neutron star or a pulsar. The first magnetar was detected in 1979, a few months after there were 2 satellites that had been deployed to study the atmosphere of Venus. These were deployed by the Soviets. They were Venera 11 and 12. They were drifting through the solar system, and they were hit by a powerful blast of gamma ray radiation. A few seconds later, Earth received a wave of radiation when that powerful output of gamma rays inundated some detectors from the U.S. Department of Defense satellites. There were some other satellites from the Soviets that were detected, and the Einstein Observatory was also hit by these inundated waves of radiation. Just before that wave exited the solar system, the blast hit the International Sun-Earth Explorer satellite. And this powerful blast of gamma ray radiation constituted the largest wave of extrasolar gamma rays ever detected. It was over 100 times more intense than any known previous extrasolar burst. The direction of that source corresponded with the remnants of a star that had gone supernova around 3000 BC. So we're talking 5,000 years ago. So although the numbers are there, it's really tough to actually wrap your brain around. These magnetic fields can wreak havoc on their local environments. They can stretch atoms into pencil-thin rods, and the dense stars can also drive these high-intensity bursts of radiation. If you were to get too close with one, say around 1,000 kilometers or 600 miles, the magnetic fields would be so strong they would not just upset your bioelectricity, rendering your nerve impulses completely useless, but they would completely disrupt your entire molecular structure. To summarize, you'd be dead. You would basically dissolve if you came within about 1,000 kilometers of a magnetar. Magnetars can also have these crazy features called starquakes. So essentially at the surface of that magnetar, which remember is just this really intense magnetically field-driven neutron star, the fracturing of that surface can cause these huge radiation outbursts, and that's what we can detect here on Earth. So we can get these high-intensity outbursts as a result of that star having a starquake, just as we can think about earthquakes here. These are not a finite life cycle of a star. These are generally only active for about 10,000 years, and then that magnetism is going to dissipate as that rotation slows and it loses angular momentum. So here are some artist renditions of those wacky things of magnetars, pulsar at the center of a supernova remnant, and then a binary system pulsar that is in the process of mass transfer and X-ray beam emission. So the final byproduct of a very massive star exploding in a supernova after the formation of iron at the core is a black hole. So it's important to think about how the media depicts black holes, how movies depict black holes, and probably how you think about black holes. So contrary to popular belief, they do not go around sucking up everything in space. We wouldn't be looking like Keanu Reeves here about to get sucked in hanging onto a pole. It's not like a hurricane. Really, a black hole is just an intense gravitational field. So in a moment we'll talk about space-time, but if we think about everything that has mass having an indent on this fabric of space, as you increase in mass, that indent is going to be greater. So if we look at the gravitational field around a 5 solar mass star, we can see the indent below, and then you could think about the surface of the star being like that. Just as if you were to hold out a blanket and you were to place a bowling ball on top of it with your friend holding the other end, but then you were to pick it up and place a marble on it. It's easy and intuitive to think about which is going to make the bigger dent in that blanket. That's synonymous to thinking about this concept of the fabric of space-time. Now, if we were to think about a black hole in this fabric of space-time, a black hole would essentially be a tear with an infinite hole in it. So we can see a much greater gravitational field around a black hole than a star, but anything of mass has a gravitational field. Before we begin talking about the properties of black holes and the gravitational effects of black holes, we have to first learn about and attempt to understand this concept of space-time. Space-time is really just a mathematical model that is fusing together the dimensions of space and the one dimension of time into one concept. This is useful in visualizing and understanding the effects of seeing how different observers perceive where and when events occur. Until the 20th century, the assumption had been that this three-dimensional geometry of the universe, describing locations, shapes, distances, and directions, was distinct from the time or the measurements of which events actually occurred within the universe. Until the 20th century, the assumption had been that the three-dimensional geometry of the universe in terms of locations, shapes, distances, and direction were distinct from the measurement of when events actually occurred within that universe. And this had implications for the effects of looking at how different observers perceived where and when events occurred. But enter Einstein and his theory of special relativity, and he looked at this concept of light, and he proposed that light had a constant value which was independent of the motion of the light source. Einstein wondered what it would be like if you could travel along with a light ray. So if you had a light ray that was shining in one direction and you traveled with it, would you observe that light ray to move, or would you observe that light ray to be standing still? This was what Einstein spent years pondering. And by the way, he was not the most phenomenal student. He actually had to repeat kindergarten. He barely got into college. He got into a very second-rate school. And he graduated second from the bottom of his graduating class in college. He would say that his gift was that he spent longer with the problem. He spent over 5 years just pondering this thought experiment that he had, that if you were traveling at the speed of light, and there was a light beam next to you traveling at the speed of light, that you would observe that light beam actually standing still. That's essentially what the concept of relativity is. So he found that the laws of physics and the speed of light must be the same for all uniformly moving observers, regardless of their state of relative motion. So for this to be true, space and time can no longer be independent. Rather, they have to be converted into each other in such a way as to keep the speed of light constant for all observers. But that this is a relative concept, and it depends on the motion of the observer. So as far as what I expect you to know about space-time, I really only expect you to understand that it is just a model showing how things in the universe can interact with other things. The details of this section are far beyond what I would expect you to be able to understand at this point. Really, if you are more interested in space-time, relativity, Einstein's theories, and then essentially Stephen Hawking's attempt to unify things, I suggest that you explore some of these things on your own, but the details of this are not something that I would expect you to know within the magnitude of this class. So a black hole is really just a region of space-time that exhibits such strong gravitational effects that nothing, not even particles and electromagnetic radiation like light, can escape from inside. So the theory of general relativity and what Einstein found is that if you have a sufficiently compacted mass, that anything can deform space-time enough to form a black hole if it is compressed small enough. So here, taking that concept of space-time and seeing how a star as massive as the sun, so one solar mass, how that interacts with the fabric of space-time, how a white dwarf of higher density interacts with the fabric of space-time, how a neutron star of greater density and greater gravitation would sink a deeper hole or a deeper dent or gravity well within the fabric of space-time, and then a black hole, which would essentially be a tear. And this is important to note because anything of mass is going to imprint or interact with this concept or fabric of space-time, and it's all going to be able to have some sort of observable gravity well, and it's all dependent upon mass. So again, to summarize, according to relativity, nothing can travel faster than light. And if light can't escape a black hole, which is the fastest moving thing that we know of, then nothing can. And as we've discussed in class, we have this concept of escape velocity, which is the velocity required to break free from an object. So we can see the relative velocities here. So the escape velocity of Earth, about 11 kilometers per second, of the Sun, 600 kilometers per second, and then at a black hole, this is the speed of light. So escape velocity is just this finite speed that one would need in order to break free from an object. And this is going to change given different masses and different distances. So the further one is away, the easier it is to break free, because if we look at mutual gravitation and Newton's laws, that's a function of radius or distance from a center of mass. So the further you are away, the less gravitational effects one would feel. But as you have an increase in mass of that body, the greater gravitational effects one would feel. So the more mass of the body, the higher the escape velocity. So much harder to escape the surface or to leave the surface of Jupiter than it is to leave the surface of, say, Earth. But if we were to look at these really low mass things like asteroids or very small moons of Jupiter, in some cases they're small enough to where if you were to jump high enough, you could actually leave it. And it would be easy to be able to throw a baseball and have it enter open space because you could eject it at a speed much higher than what that escape velocity would be. So black holes have these regions known as the event horizon, which is associated with the escape velocity. So any matter that crosses the event horizon then is completely bound to the black hole and is essentially past the point of no return. Or we could say what happens in the event horizon stays in the event horizon. So this is the point at which the escape velocity is equal to the speed of light. The Schwarzschild radius then is the radius that defines how big the event horizon is. And this is associated with a quantity of mass. This was calculated using Einstein's theory of general relativity in 1916, so really long time ago. So for example, if we were to take the current radius of our sun, if it were compressed to have a radius of 3 kilometers, it could then be a black hole. So the Schwarzschild radius is the radius at which any object could be compressed in order to be a black hole and have an event horizon in which the escape velocity is equal to the speed of light. So here we can see that physical boundary of the event horizon, and here would be the Schwarzschild radius, which would just be the radius from the point of the singularity out towards the edge of the event horizon. Again, this is set by mass. So in order to actually have a black hole, you have to have a star of extreme mass in which nothing can uphold the stability of the star after that collapse of the core. So there's nothing that can balance that out. So you have this core that collapses to a singularity. All of the gravity is then concentrated into a single point, and even light then would be trapped. So a big takeaway here is that any object, if it were compressed small enough, could become a black hole. So every one of these dots corresponds with the object to the right. And if its current size were compressed to this size, it would be a black hole. So if Earth, with a radius of about 6,700 kilometers, were compressed to have a diameter of 18 millimeters, this big, it would be a black hole. The moon would be this little pixel, and Pluto would be this tiny little pixel. One of the effects that astronomers think would happen if you were approaching a black hole is called time dilation. So what this means is that if there were an object that were approaching the event horizon from the observer's side, they would appear to slow down and never quite pass through the horizon. But the image would become more and more redshifted as time elapsed, until eventually that person would appear to just disappear. So what that means is that the wavelength is getting longer and longer as the object moves away from the observer. And then the traveling object, however, would experience no strange effects and does in fact pass through the event horizon in a time that appears to not be affected at all. So what we could see, if at time 0, then as that object is approaching the black hole, it would appear as though they just then come to stand still. And that would be the point where, as they're crossing the event horizon, their velocity would be equivalent to the speed of light. So it tends to distort the observer's perception of an object or person or star that would be approaching a black hole. But if you were that thing or person or object, you wouldn't perceive that change at all. What I think is one of the coolest things to be observed gravitationally is this concept of spaghettification, in which your body would essentially be compressed to a single stream of atoms as it approached a black hole. So say you decided to go in feet first, with your feet closer to the black hole, the gravitational pull on your feet would be larger than that on your head, and it would essentially rip you to pieces, or any side that happened to be closer. So say there were an observer observing this astronaut approaching the black hole. As the astronaut was elongated and stretched to a single stream of atoms, the wavelengths emitted as that astronaut would cross the event horizon would be longer and longer. So infrared, then microwave, then radio. So any observations of this would have to be detecting those wavelengths, not looking at the astronaut himself. So that's another way that we can observe black holes, is the detection of matter as it infalls over it. And also that matter can then be excited to X-ray wavelengths, and those would be some of the jets we see in that glow that appears along the event horizon, glowing in X-ray, not optical. And here we can then see the concept of time dilation, so that if we had two clocks here, one on normal time, one that is traveling close to 0.99% of the speed of light, we could see that in the same given amount of time, that this clock would run faster than the one approaching the speed of light. The clock that is approaching the speed of light would run slower. So here's a visual of a star approaching a black hole, and what would be detected as that star approached a black hole would be the X-rays, and there would be an effect, a gravitational effect on stellar motions. So those motions would then be erratic, and an accretion disk would form that would emit X-rays as stars would be ripped apart gravitationally as they cross that event horizon. So here is just an artist's rendition of a star being ripped apart by a black hole. And I know these lists were long, guys. I apologize. Please remember that neutron stars are a bit more straightforward, and I would expect you to know a lot of the details, applications, and the why. Whereas with black holes, it's a lot of information. It's new information. I do not expect you to know details of relativity. I do expect you to know more the what, not the why. So the general features, not necessarily the background. And I don't need you to necessarily understand deeper applications of black hole science. See you in class.